There's many reasons why scientists are so interested in studying radioactivity. One of them is that it gives us clues about what's going on inside atoms. So by studying particles that get fired out of the atom, which is what radioactivity is, it lets us know what's actually going on inside the atom. And this has been really important to give us clues about what's going on inside the atom so that when we're trying to build up a model of what the atom looks like, we've got all these clues, and radioactivity gives us a lot of these clues because we can't really go and look at atoms directly. They're far too small for us to see with microscopes. So we just have to use these clues to build up a picture or a model of what the atom is like. Another reason why we're interested in studying radioactivity is so that we know how to safely deal with it. Radioactivity can be found in all kinds of places, and if you don't know what you're dealing with, it can potentially be dangerous, as we saw with Pierre and Marie Curie earlier. Radioactivity gives us a lot of medical treatments, particularly in the treatment of cancer, using radiotherapy, which is essentially using gamma radiation to try and zap, if you like, cancer cells. And again, if you want to be able to do things like that, you really have to know what radioactivity is and understand it inside out. But there are also many other applications of radioactivity, and we're going to take a look at a few of them now. Some really clever things that people have come up with. One of them is the simple fire alarm. Now, we might think it's simple, but it's far from simple, really. There's a very simple idea made clever, if you like. Okay, let's take a look at what's going on inside a smoke alarm. So this here is a smoke alarm. I'm just going to let you have a quick look over that diagram yourself there. Have a quick look at it. Okay, so what's going on? Well, obviously on the outside, we have this plastic casing. So in your fire alarm, stuck to the roof usually, in your hallway maybe, you've got a plastic casing on the outside. Not really important. What is important though, is that it's got like some kind of a grill in it. So it's got some slots or holes to let things through, let things onto the inside of the casing. That's important. Another thing that's really important is this here. We've got this alpha radiation source. Now, we already know what a radioactive source is. It's just a sample that contains a lot of radioisotopes. And what alpha source do we use? Well, we use this isotope, and this is important because we need to remember this. We use this isotope americium 241. So americium-241 is the alpha source that we use in these smoke detectors. Now, how does the smoke detector work? Well, this here is our alpha radiation source, and this here is a detector. And the detector is constantly checking, is it getting hit by alpha particles, basically. And so long as it is, then the detector is connected to this circuit. It goes off to the alarm. And so long as this keeps happening, alpha particles keep hitting it, then it will be fine. The alarm will not go off so long as alpha particles keep hitting it. That's what keeps the alarm off. Alpha particles going from the source and hitting the detector. But very cleverly, we've already learned that alpha particles have a really low penetrating power, which means that this gap here has to be really small for a start. So there's not much space in between this. But if anything was to come in between these, then it might stop the alpha particles from reaching the detector. And that's exactly what happens if there's a fire. If there's a fire, we get smoke particles, and the smoke particles essentially, and this is why it's really important that there's holes in the casing, the smoke particles, as we can see here, can enter the casing and basically block the alpha particles from hitting the detector. And once the detector detects that there's no alpha particles, that there's alpha particles being stopped from hitting the detector, then it sets the alarm off. So very clever use of the fact that alpha particles have a low penetrating power. We've used this to our advantage as humans to create a technology which saves loads of lives. So really important development or technology. So we're just going to make a little summary of this. Okay, so on this table, and I suggest you do something similar. Maybe do it at the end from memory if you can, okay? So here what we've laid out on the left-hand side here are the three types of radiation, alpha, beta, gamma. In the middle row, we have the source. So what are the source of alpha particles, and then what's the use? So we've just seen the source, okay? Hopefully you remember what that was. If you do, pause it and write it down now. Okay, hopefully you're written americium 241. That's our source of alpha particles, and the use is it's used in fire detectors. Okay, so it's alpha particles. You do need to know basically a source of alpha particles and where it's used. So this is exactly the information you need to know. So I do suggest that you have a copy of this. Okay, so that's alpha. What about beta radiation? Beta radiation, where do we use it and what's the source? What this person is doing here is they are taking a sample of bone and they're going to do some analysis on it. And what they're looking for is to find out how old is this bone? How old is this sample? And they do this using something called carbon-14 dating. This is how it works. Here we have a sample of carbon. Carbon is found in all living things, okay? And there are two main isotopes of carbon. We've got carbon-12 and we've got carbon-14. And while an organism, a living thing, is alive, the amount of each of these stays relatively stable because we're constantly breathing in carbon dioxide and plants are constantly producing carbon dioxide. And so long as the organism stays alive, the ratio of these things stays approximately the same. So in this case, we have 15 carbon-12 atoms for every 10 carbon-14 atoms. And that's around the ratio we would expect to find in an organism while it's alive. Now, it might go a tiny bit up or a tiny bit down, but approximately those should be the pretty steady ratios. And so long as the organism stays alive and keeps breathing in carbon dioxide and breathing out, plants produce carbon dioxide, this is the approximate amounts of carbon-12 and carbon-14 they have, that ratio, 15 to 10 or 3 to 2. Of carbon-12 to carbon-14. That's fine. But what's important here is what happens when the organism dies. Once the organism dies, it's not doing gas exchange anymore. It's not taking in new carbon atoms in carbon dioxide. So it's not replacing any carbon-14 atoms that might decay because carbon-14 is radioactive, which means it decays. So once the organism dies, when the carbon-14 decays, as it's doing even when it's alive, it's not being replaced anymore because we're not taking in carbon from the atmosphere anymore. So once it dies, I suppose this is in a living organism and this is in a dead organism. Once the organism is dead, the carbon-14 atoms decay to nitrogen-14 atoms, okay, by beta decay. All right, so it goes from carbon-14 to nitrogen-14. And obviously you can see now that there are less carbon-14 atoms. They are not being replaced. So we're down now to 55 carbon-14 atoms where it was 10. So half of the radioactive nuclei have decayed now. We've gone from 10 down to 5. How much time did this take? Well, we know what this amount of time is called. We've gone from 10 to 5, so half of the nuclei, the radioactive nuclei, have decayed. So what we say here is that one half-life has passed. So if we were to measure a piece of bone and it looked like this, it had this ratio of carbon-12 to carbon-14, we would know that one half-life has passed since the organism died. So how many years is that? Well, scientists know that carbon-14's half-life is 5,730 years. So by measuring the amounts of carbon-12 and carbon-14, scientists can work out how many years an organism has been dead. So that's how scientists do carbon-14 dating. All right, so let's go and check this out in our table again. So what was our source of beta particles? Our source of beta particles was carbon-14. And what is it used for? So again, hopefully you can pause the video and write down the use of beta particles here in carbon-14. Pause the video, do that now. Okay, so you should only be playing if you've actually tried to do that, pause it and write it down. We'll use it for very simply carbon-14 dating, finding out how old things are. All right, let's look at some gamma radiation now. Where do we use gamma radiation? This is probably the most useful types of radiation. All right, here we have a sample of strawberries. Okay, now What's going to happen after, say, a certain amount of time goes, say we wait for 5 days, what's going to happen to them strawberries if we don't eat them? What's going to happen is this. They are basically going to rot. Okay. If we just leave them in, pick strawberries off the strawberry tree or whatever they grow on, think strawberry bush maybe. If we just leave them for 5 days, they're just going to rot. Now, why do they rot? They rot because bacteria feed on them. So bacteria will basically eat them and break them down. They start to digest them. And that's what's going to happen if we just leave them for 5 days. But what happens if instead of just leaving them for 5 days, we treat them with gamma radiation like this? So we treat them with gamma radiation. What gamma radiation does is it essentially zaps the bacteria, if you like. It kind of kills them, but this is the important thing. It kills them without heating up the food. That's why we cook food. We cook chicken to kill bacteria that's in the chicken or on the chicken, because that's what makes it safe to eat. We can't really cook strawberries. Nobody wants to buy strawberries off the shelf in the supermarket that are cooked. Nobody wants that. We want fresh fruit, fresh vegetables. So by using gamma radiation, we can have a situation where after 5 days, the fruit is still perfectly okay. And in fact, it might be 10 days later, it's still okay. Because the gamma radiation has essentially killed any bacteria that were on the fruit. Has killed the bacteria. Okay. Now, like I said, another way you can kill bacteria is to use heat. That will kill them, but nobody wants cooked strawberries. So this is what the fruit would look like after 5 days with no irradiation. So no gamma irradiation. And this is what it would look like after 5 days after gamma radiation. So gamma radiation is a way we can prolong or preserve shelf life. It can be stored for longer. This is good for producers and it's good for customers who are buying things and don't want to throw food out after a few days. So it creates less waste. It lets us store it for longer. And obviously it allows us to not have to cook fruit or veg. Another really important use of gamma radiation is for things like this. This is medical equipment. It's really important that medical equipment is sterile. That means there's no bacteria on it. If there's bacteria on medical equipment, so they use it on one person, they don't properly clean it and they don't make sure it's sterile, they use it on another person, that's what causes diseases to transfer in hospitals. Not a good idea. Now, lots of medical equipment has bits of rubber in it and have bits of plastic. So again, we have the option here. We can kill bacteria by using heat, but much medical equipment has rubber and plastic and stuff like that in it. It's too delicate to like put it in an oven and heat it up, or put it in somewhere where it's really, really hot. And washing loads and loads and loads of medical equipment can just take too long, and it's not as effective anyway, washing. So again, in that case, we can use gamma radiation. So use gamma radiation. So put this into a container, put it in a bag into a container, and just zap it with gamma radiation. And again, this causes the the medical equipment to be perfectly sterile, and it can be then used on a new patient without transferring any disease. All right. The best source of gamma radiation is an isotope called cobalt 60. Cobalt 60 is a really common and important isotope in the use of gamma radiation. So that's where we can get these gamma rays from. All right, let's go back to the table now. All right, so pause the video and hopefully you can write down what the source of gamma radiation is. So pause the video and do that now. Okay, so you'll only be playing if you've written down beside gamma here what the source of gamma radiation is. I said it just before this, it's cobalt 60. Okay, and what about our uses then? Our uses of gamma radiation. So gamma radiation can be used to irradiate food. So food irradiation, which just means to treat it with gamma rays to make it last longer. And it can also be used to sterilize medical equipment. So two really important uses of gamma radiation. All right, so hopefully you have that full table taken down now. It's an important thing to try and learn and remember. Hopefully after drawing out and showing you each of the uses, it's something that might stick with you, but ultimately you guys have to learn this, okay? Common questions on the exam. So now we're ready to do some questions. So I want you to do questions 165 to 174 that come in the booklet here. If you're not following along with our booklets, you can go ahead and pause it and do them from the screen here. Otherwise, you can go ahead, open up the booklet and do the questions from there. We'll see you in class next day. Thanks, guys.